welcome to this section of the course. In this chapter, we'll be learning about integration. Now, from what you remember I said at the beginning of chapter with differentiation, integration is the opposite side of the coin to differentiation. But I've got good news for you. There is no integration from first principles, so there is less algebra and less proofs in this chapter, so it's rather more straightforward, and I look forward to teaching you this section of the course. Alright, these are the topic areas, and I'm not going to read it out for you. You can read it for yourself, and let's get to it. Alright, so my very first initial lesson is always about showing you, testing your prior knowledge. So pause the video, have a go at these questions, and then I'll show you the answer once you've had a look at them, once you've had a go at these questions. So pause the video, have a go. Alright, I hope you've had a go at these questions by now. Simply just go and rewrite each of these with the power rule and add their indices together. So 3 minus a half is 2.5. So 2.5 can be written as 5/2. Add the indices on the top of the fraction and subtract the index from the denominator. You end up with 3/2 for the index, and the 2 in coefficient of x remains as it is because the 2 didn't cancel away. The next part, part C, involves you writing two terms and simplifying two different terms. So the top of the fraction needs to have two difference. So you can split up the fraction as x cubed over the square root of x and x minus x. So you could split it up like so, and then you'll subtract the powers. If there is no power, it's a 1. It's not visible for you, but it's an invisible 1 there. So once you subtract the powers, you end up with 5/2.5. So you do the same trick for the next part, you end up with this answer. And for question 2, you just have to test. This is testing your differentiations. So you just take away you multiply the powers by the coefficient. 3 times 2 is 6, and 3 minus 1 is 2. So you write 6x to the power 2, and the 3 remains, the x just disappears. So then the next one, bring the 2 down at the front, multiplying 2.5 will cancel both away, and x remains with power of 1. And the other negative x becomes minus 1. First, for part C, multiply out the bracket, you get x cubed plus x squared, then differentiating x cubed plus x squared gives you this. Again, split up the fraction and differentiate after. Here we're sketching the graph, so write the roots. Roots are plus 3 and minus 1, so you write it like so, and you substitute 0 for x to find the y-intercept. This is a cubic graph, positive version of cubic graph, so with a repeated root at x equal to minus 1. So it should bounce from the bottom off here at minus 1. Actually, no, the other, this one, minus 5 is to the left, so actually it will go through minus 5, and it would be something like so. Minus 5 would be here, and minus 1 would be here. So my apologies, let me rub that off. So there is not a, yeah, it should look something like so. Okay, with the tangent being at minus 1. So there, like so. Alright, so I hope you've had a go at these. Now, I do want to also introduce integration to you. So I am going to pause the video. As I said, yes, here we are looking at the definition of integration. In a nutshell, if you have a rate of change and let's say you have, we start off by first integrating rate of change. If you had a derivative, had found the derivative of a function, and now you want to go back to the find what was the original function, you integrate it with respect to its variable. F was written in terms of x, so now we integrated with respect to x, the f dash, or the first derivative here, the answer will come out as the function itself. Now, yes, there is a little adjustment, plus c and minus c, I'll explain that later, but in a nutshell, integration is the reverse of differentiation. And you use just this letter dx to say that this is not a multiplication anything, it's just like a notation. These two, this this is like a s, long s notation. Some say that it's because it's some sort of a summation, really. What we're doing is we're summing up these areas under the curve, all right? So that's one way of thinking about it. Now, what integration I've written here for you is like multiplying a rate by the basis of the rate. Now, let's say you've defined velocity or speed. I should have used the word velocity, but the velocity is defined in terms of t. So let's say it has some formula like t squared plus 5t minus 4. And when you integrate with respect to time, whenever you put this sign in front of it, that means you're integrating it, all right? It's written in terms of t, so whenever you have an integral sign, you must have some letter telling you that integrated with respect to t. This dt means just integrated. So what comes out here is, out of this operation that I will teach you to perform, is as if we multiplying this velocity by time. So the result, when you evaluate it properly, if it's a definite integral, will be the distance or displacement, all right, distance traveled, all right. So because we are integrating with respect to time, it's not exactly multiplying by time, but it is as you see this graph here, it has velocity on the y-axis, so its velocity was just a stable rate of 10. So when you integrate 10, you end up, and you need to have also, we do care about this of the integrals. It was going from 0 to 8, so you would have put 0 to 8 there, and if you integrate that with respect to time, you will get 10t, and then substituting 0 and 8 into it, you would end up with 80. You will end up with this result. I'll teach you more about it, but the point is just to get an overview of. I'm not teaching you the details of what function, what to do. I'm just telling you what it's all about. So it's apply. If you integrate acceleration formula, you end up with velocity, and it has other applications in electronics, calculating voltage, power, time, capacitance, and whatnot. I'm not teaching you physics here, so we'll overlook that. But just I'm just trying to motivate you that there is a lot of applications in sciences for integration. Let's get to it. All right, I'll see you in the next video.